Olá, welcome everyone to the first seminar of this year of 2026 of the Priberam Lunch Seminars. And today we have Teresa. She works for us at Priberam, and she finished her PhD recently, last year, and won the Spark Award of the Center for Responsible AI with this work that she's going to present. Teresa, the floor is yours.
Okay. Hi everyone, can you hear me well in the back? And at home as well? Okay, so I'm going to present to you a work that, thank you, that is that I developed as part of my PhD that I finished last year. My PhD was on fairness in machine learning with a focus on federated learning. And this work, this is joint work with Professor João Gama, Professor Helder Araújo, and Professor Pedro Henrique Jabreu, and it was recently published on IEEE transactions on neural networks and learning systems. So this is what I'm going to talk about today. I have a big section on the background where I'm going to cover group fairness, federated learning, and concept drift, which are all important for understanding this work. Then I'm going to present in section 4 the motivation of this work and why we should study group-specific distributed concept drift. In section 5, I'll introduce the formulation and our approach. In section 6, I'll present the experiment, and I'll finish up with some conclusions and future work on this work. So let's start by talking about group fairness. Who is familiar with the concept of group fairness? Okay, I see some hands. Before I tell you what group fairness is, I'm going to show you two real-world examples of unfairness in machine learning in the real world. And I'm going to start with the Compass case, which some of you might have heard about. For those who don't know, Compass was a tool used in United States courts to assess the likelihood of a criminal to commit a new crime again, which is to predict the recidivism score. And what was found was that this tool overestimated the risk for Black defendants, while it also underestimated the risk for white defendants. And this means basically that the false positive rate was higher for Black defendants than for white defendants, while also the false negative rate was higher for white defendants than for Black defendants. And to give you an example, we have here two defendants, a white defendant and a Black defendant. And what this tool predicted for the white defendant was that it had a low risk of committing a new crime again. But what we saw was that it went on to commit a new offense. At the same time, we have a Black defendant where the tool predicted it had a medium risk of committing a new crime again, but it did not commit a new crime again. So this happened on the general level. So can you hear me well? So we can say that this tool was discriminating people based on the sensitive attribute race, okay? Which is, of course, not what we want when we apply machine learning in the real world. Another example of unfairness in machine learning in the real world was of a tool, a recruitment tool used by Amazon and developed by Amazon, which filtered out candidates' CVs that they submitted to the company to work at Amazon. And what was found was that this tool discriminated on the basis of gender. There was a real example of a woman where her CV said that she was the women's chess club captain, and instead of increasing her score, the tool was penalizing that woman just because it contained the word women's chess club captain, just because it contained the word women's. If you remove the word women, it would increase the score. Why did that happen? Well, this tool was trained on data of people that were working at Amazon, and since the majority of people working at Amazon were men, this tool learned to discriminate against women, which is, again, not what we want. So this tool was being unfair with respect to the gender. So now that I've talked about two examples of unfairness in machine learning in the real world, let us define what group fairness is. But group fairness is a broad term, but it can be understood by the idea that algorithms do not disadvantage groups of the population with respect to sensitive attributes. And sensitive attributes are human characteristics that carry legal, social, or ethical significance. So they are human attributes where it's illegal or unethical to discriminate against. And what happens is because of harmful biases present in the data, in the model design, or even in how we carry our evaluations of the models, there are some groups defined by these sensitive attributes, which we call unprivileged groups, that receive fewer favorable outcomes by the algorithm because of these harmful biases. So how can we evaluate group fairness? We can do that using group fairness metrics, which compare how different groups defined by these sensitive attributes are treated by the model. And they can evaluate fairness by checking whether performance, errors, or prediction rates are similar or not across these groups defined by these sensitive attributes. So we can check the ratio of true positive rates, for example, of two groups, the difference, and sometimes more than two groups are considered. We don't always have a binary sensitive attribute. It is important to note that no single metric fits all cases. The right choice of metric always depends on the context of where the algorithm is being applied and on the stakeholders involved, both the ones developing the algorithm and the ones affected by the algorithm. But to give you an example of a group fairness metric, I have here a scenario of an algorithm that either rejects candidates or accepts candidates. In this case, we consider the sensitive attribute to be a color, and we have a binary sensitive attribute that can be two colors, blue or orange. Among those candidates, we have qualified candidates that should be accepted or could be accepted, and we have unqualified candidates. And in this case, qualified candidates in both groups have a 40% acceptance rate. So this this algorithm satisfies equality of opportunity, which is a widely used fairness metric. So now that I've talked about group fairness, let us shift the topic to federated learning, which is also important for understanding this work. So federated learning allows multiple clients to learn a shared machine learning model together. So what happens is that we can have a central server and multiple clients that are learning based on their data. So instead of sharing the data to a central server, each client trains their own local model locally using its own local data. So this, it's okay. So this enables the client's data to remain private at each edge, which is the main motivation for federated learning. It is for privacy reasons. So the first work on federated learning is called federated averaging, and it consists of a way of periodically averaging these client-trained models together. So what happens is that the server starts by initializing a global model theta and defining the number of communication rounds. And then for each communication round, the server selects KT, which is a random subset of clients, to participate in that federation round. And then what happens is that each client will train its local model using its local data, doing, for example, gradient descent. Then the server sends the model back to the server, which then aggregates these models together by averaging them with weights proportionate to the client's data sizes. Okay, so this is called federated averaging and was the first federated learning algorithm proposed. While it works surprisingly well, it has some disadvantages, as we'll see later. So there are some challenges in developing federated learning algorithms, and the first one being that clients often have heterogeneous data, which is non-IID data, meaning that their distributions vary significantly. And prior work has shown that this statistical divergence or heterogeneity can cause gradient divergence, which can make models unstable to train. Besides that, ensuring fairness in federated learning has been gaining increasing attention. However, because of the inherent federated learning challenges, it is more difficult than to develop it on a centralized learning scenario. So non-IAD data may cause models to become more unfair. We have restricted information of the sensitive attributes at the server level because the client is not able to share the data with the server. And the aggregation algorithms that we choose may also cause unfairness in the global model, because one of the clients may have a very low representation of a minority group that is also a privileged group, which makes it hard for the global model to learn those statistical patterns that are present in that client. And if the client is dominating the federated learning scenario because it has more data points and we are giving more weight to the clients that have more data points, then it becomes difficult to learn information about that minority group. So all these challenges make developing fair federated learning algorithms already difficult. When we mix that with concept drift, we have an even more complicated scenario, which is what I'm going to talk about, which is the concept of concept drift. So for those who don't know, concept drift refers to a change in the relationship between the input features X and the target variable Y over time. To illustrate that, we have here an original data with two labels, red and green or yellow, and we have a decision boundary. And what happens in real concept drift, which is what we are interested in, is that this decision boundary may change. So in real concept drift, the conditional distribution of P of Y given X changes over time. So some patterns that the model has learned previously may no longer hold, and the model needs to be updated to account for these changes. So concept drift in federated learning is difficult because this concept drift may appear staggered in time, both in time, like I said, and also in space, because we have different clients as well. So this is also known as distributed concept drift and has been studied before and is the basis for our work. However, this work is not about fairness, and our work is about fairness. So before I move on, I just finished the background section on group fairness, federated learning, and concept drift. And I would like to know if you have any questions before I move on to the work. Yeah. Yeah.
My question is against like the rules of federated learning if you know that certain model has specific rules.
Okay, you can share. Some clients may share some information, demographic information with the server, but that of course can violate privacy. But you are always allowed to share those statistics with the server, and the server can make some decisions on the basis of that. And many works do that. Our work also shares some of doesn't share the statistics, but it will share the losses of the model, which is of course some information that some malicious agents might take advantage of. But if you use privacy mechanisms like differential privacy, you can attenuate those drawbacks that we have when sharing this type of information with the server. But that is a very good reason. And yes, some fair federated learning algorithms are developed on the basis of those statistics that we can share with the server. Thank you for your question. Do you have any more questions about group fairness, federated learning, concept 3? Yeah. So concept drift, you can identify it by looking at the losses of the models. If they decrease, it means that probably we had a concept drift. You can also try to infer the statistical patterns of the data. But what is done in practice is looking at the losses of these models over time. Outliers. Yeah. Sometimes it is difficult to know if this drift that happened was just a one case or if it's here to stay. So yeah, there are works that have explored those difficulties. Here we don't look much into that because, as you'll see, here in a time step we receive quite an amount of data. So we don't look at an example at a time. It's not an online setting. It's more like at each time step we receive new data and we train on that data. So this problem is not as a problem in our scenario, but that is a very good question. But it is more focused on streaming settings, and here we are not covering those streaming settings. But thank you for your question. No more questions before I move on? Let me just drink some water. Okay, now that we've talked about those concepts, I think we're ready to the motivation of our work, which is why should we study group-specific distributed concept drift? And to illustrate, I'm going to give you a scenario where this might happen. So imagine a federated learning systems where different hospitals are operating as individual federated learning clients. And we can imagine if hospital one or client one introduces a new treatment that causes side effects for Black patients. So this new treatment can cause group-specific concept drift because it affects only a specific demographic group and is happening also at a single client. At the same time, the same type of drift or other types of drift may be happening in other clients as well. So this is the problem of group-specific distributed concept drift, which we are the first to introduce and formalize in the literature. And we also develop an algorithm to tackle this drift, which is what I'm going to talk about after. So before I talk about the algorithm, let me explain different scenarios of concept drift that may happen in a federated learning scenario. In this case, I'm not sure if you can see it, but we have 10 different clients participating in the federation. We also have 10 different time steps, okay? Within each client, we consider a binary sensitive group, S0 and S1, where each client has two rows that correspond to the two sensitive groups. We also consider, in this case, three different concepts, A, B, and C, which corresponds to the concept drift. So in the first scenario, there is no concept drift, meaning the underlying data distribution does not change for any client, for any group, and for any time step. In scenario one, we have general concept drift, meaning that all clients experience a uniform concept drift in the data distribution over time. So clients 1 to 10 suffer concept drift here at time step 3, where the concept changes from A to B, then it changes to C, then back to A, so this is a reoccurring concept, and back to B again, okay? And this is called general concept drift. Then we have distributed concept drift, which has been studied before, where each client experiences changes in their local data distribution over time. So here we can see that the drifts are staggered in time, but also in space, because different clients are experiencing different concept drifts, and these drifts might be reoccurring and happening at the same time at different clients, okay? So this is difficult to handle already. Then in this work, we first introduce group-specific concept drift. In this case, it is general, because groups within each client may suffer concept drift. In this case, only group S0 is suffering concept drift, while group S1 remains in the same concept, okay? But all clients are experiencing the same type of group-specific concept drift. And finally, we have group-specific distributed concept drift, which is the main focus of our work, where groups within different clients experience concept drift at different times. And the scenario that I showed before of the hospital, I think it illustrates what can happen in these federated learning scenarios. Do you have any questions about this? Is it clear? No? Okay. Okay. So, like I said, we focus more on scenario 4, even though we also introduced only the group-specific concept drift, as it has never been studied before. So what happens is that conventional drift detection algorithms that rely solely on the overall loss metric may struggle to capture this kind of drift because it is group specific, especially when the unprivileged group that is suffering this kind of drift is underrepresented in the dataset. So the overall loss metrics may not capture these subtleties that are happening in specific groups that might be a minority. So this demonstrates the need of incorporating group-specific loss monitoring over time at each client, which is what we do. So I'm going to present now the formulation and our approach. We consider K clients over T time steps, where each time step, like I said before, corresponds to an interval in which a client receives new private data. Each time step is composed of R communication rounds, which is where the client sends the model back and forth with the server. And we focus on a classification setting where X is the input space, Y is the output space with C classes, because we have a multi-class classification scenario. Y hat denotes the predictions, and S is a binary sensitive attribute. And like I said, we recognize that it is not always the case that these sensitive attributes are binary. But to simplify, we consider it binary for the sake of simplicity. So our algorithm, which is called fair-fed drift, offers a solution to this challenge, to the challenge of group-specific distributed concept drift, and its strategy can be decomposed into the following steps. First of all, we consider a multimodal approach. Then we incorporate at each client group-specific concept drift detection, which is local. We have a global model merging step, and then we perform training and model averaging. I'll explain these steps in more detail in the next slides, but first of all, let me present the optimization objectives followed by our approach, which is that for each global model in the set of global models, because we will have multiple global models, we will minimize the sum of the error functions of the clients that have identified with that model, and the client identifies with the model if the sum of group losses of every group S in S, and then for each group S in S, the consecutive loss differences between a time step and the time step before does not surpass the threshold for that group, which is delta S. This might be a bit confusing, but I hope with the pseudocode that I'm going to show, it will be more easy to understand that this is the objective that we are trying to follow. Yeah. So this is model theta. I'm going to maybe talk about everything. So this is model theta M in the set of global models. K is the clients. Yeah. T is the time step that we are considering. WK of T is the identity of a client at a given time step. And this is the loss. This one. This is a sensitive attribute in the set, a sensitive group in the set of sensitive groups. So in this case, we only have two. And this is the loss, and this is the data set of a client at a given time. And I think that's it. I'm sorry, I didn't go much into the details, but I hope it is clear now. So first of all, like I said, we adopt a multiple global model approach. Why? Because the core idea of this algorithm is to recognize that a single global model cannot adapt to all these concepts. So we use multiple global models where we aim to have one model for each concept. By concept, I mean like A, B, C, like I showed before. So what happens is that in the beginning of the federation, there is a single global model and all clients are associated with it. So we make one assumption, okay? We assume that at the beginning of the federation, all clients and all groups are in the same concept, okay? And this is, of course, a limitation of our approach. Then we incorporate a group-specific concept drift detection at each client, and a drift is identified at the client if there is no global model in the set of global models where for any group S in the set of groups, the difference of losses of 2 consecutive time steps is smaller than the threshold for that group. So basically, if the loss for a group decreases a lot, more than a threshold, we say, okay, we have identified a group-specific concept drift, okay? And then we do that for every global model in the set of global models. So in the case there is no fit model for that client, then a new global model is created and that information is shared with the server. Then we perform global model merging. Why? Because different clients may be experiencing the same type of group-specific concept drift at the same time step. So we need to merge these global models together. And this operation is a bit complicated, but it basically involves the creation of a distance matrix. And this merging process iteratively merges the two closest global models together. So it performs an hierarchical clustering procedure to merge the closest global models together based on the losses of every client and every group on all of the global models that is also shared with the server. And finally, we need to train and average these global models together. And this process involves our communication rounds. And basically at each round, each client K trains its own local model theta M of K, if it had associated with that model M up until that time step. And here we can consider a sliding window of W steps. And basically, these local models are aggregated by the server to update each global model. So this is a diagram of our approach. I'm going to repeat basically what I said, but hopefully make it more clear. In step 0, okay, we have a server and we can have multiple clients, okay, participating in the federation. Here we only have a single client for demonstration purposes. But basically, in step 0, the server sends its current global models to each client. Here we can see that we have 3 current global models, one red, one blue, and one green, and all of them are sent to the client. Then in step 1, each client will make predictions on those models with its current data. And then each client will choose the best model based on those predictions. If we don't have a model that is good enough, it means that we have detected group-specific concept drift, and then a new model is created. All of these losses and information of whether concept drift or not happened is shared with the server in step 3. Then in step 4, the server merges these global models together that correspond to the same concept. In step 5, the clients will train their models according to their identities up until that time step. And then in step C, these models, 6, the clients send these models back to the server. And then in step 7, the server averages the models together, okay? So now I'm going to talk about the experiments performed. So we test our approach in diverse data sets, NIST, feminist, Sci-Fi 10, and about. Since we didn't have, or we are not aware, or we have not found yet real-world data sets with this kind of drift, we needed to simulate this drift to perform our experiment. So to do that, we partition each data set into K clients and T time steps and introduce group-specific concept drift at specific time steps. And we designed 5 different scenarios of group-specific concept drift with 5 different concepts, A to E. So scenario 1 is the simplest one, while scenario 5 is the most difficult one. We consider the following group fairness metrics. The first one being accuracy equality, which compares the accuracy of 2 demographic groups. Then we have overall equality of opportunity, which compares the true positive rates for all classes because we have a multiple classification scenario. And it does the ratio of the 2 groups. And finally, the overall predictive parity that compares the positive predictive values for 2 groups across all classes. We also experiment with different levels of data heterogeneity using a parameter alpha, where the data, where heterogeneity here means the size of the unprivileged group relative to the privileged group. So how well represented or not is a group within the compared to the other. So the results demonstrate that our algorithm, fair drift, is able to achieve good fairness outcomes without degrading accuracy much. And interestingly, a fair drift results closely resemble those of an oracle algorithm. Basically, oracle knows exactly where the concept drift is happening and already creates the clusters of models based on that. So it is an upper bound algorithm, but it is not realistic. So it is interesting and good that fair drift closely resembles the results of that algorithm, meaning that it is able to create the clusters that we want correctly. We perform other relevant experiments. We perform experiments with the unprivileged group size, the effect of delta S, which is the threshold of group-specific concept drift detection. We also experiment with different window sizes, the effect of scenario complexity, if there are more drifts or not occurring. And we also do a comparative cluster creation with other baselines that also perform this multiple global model approach. The conclusions of our work. So in this work, we formalize the problem of group-specific concept drift and its distributed counterpart. We create an experimental framework for studying this type of drift, and we develop an algorithm to handle this type of drift. So what we found is that if the algorithms are not looking at these group-specific patterns, that fairness can decrease. The efficacy of fair drift in terms of fairness is also demonstrated in our experiments, and future work should focus on mitigating the communication overhead that happens in this algorithm, because we are always exchanging lots of information between the client and the server, and we want to minimize these communication costs. Also, we make the assumption that at the first time step, all clients are in the same concept, which is of course not ideal as well. So this is the future work that is planned. And that's it. Thank you. Do you have any questions? Yes. Oh, nice.
Sorry. So two questions, one related to the other. So the first thing is, it seems to me from what I've learned here today is that it's key for your whole algorithm, the threshold that you specify for identifying concept drift.
Yeah.
So you can either have it too high and you never identify it, or too low and you define a model for each client.
Yeah.
So the first question would be, I suppose you can tune this according to the fairness metric that you specify before the experiment.
Yeah.
But my question would be if you have any thoughts on this, or if there is another way to choose, or any implications of choosing the right threshold. And the second would be,
Can I just reply to the first question first?
sure, but they are related.
Oh, okay.
I mean,
sorry.
let me just shoot both. The other would be, if you do choose a very narrow threshold, I suppose you would be you'd end up training a model for every client, or something very similar to that. That actually doesn't ensure any fairness, because you might still have one model overfitting that client, and then just averaging out what you learned from one specific client. What would be? I mean, this is just a comment. I don't know if you have any thoughts on this.
Yeah, of course. Thank you so much for the question. It is very interesting. So basically, what we needed to do was basically find the right threshold for that given data set. Okay, and we assume the same threshold for all clients in this case. So ideally, we would not need to tune this threshold. We would not need to find this threshold. It could be automatically found. And also, ideally, different clients would have different thresholds depending on the amount of data from the unprivileged group that they have. because it might be more noticeable or not in certain groups. So ideally, that is a good idea for future work, would be to automatically find this threshold delta S. So thank you for the question. Did I answer it? Okay. So we perform experiments on the delta S, which is the threshold parameter here, on different data sets and on different levels of heterogeneity. And that's how we find the best threshold for that given data set under those heterogeneous conditions. But ideally, it would be automatically found. Thank you for the question.
Hello, I have a question. Thank you for the nice talk.
Thank you.
So can you go back to the big pseudocode? Or the other one is okay.
Okay.
So when we initialize what you call global models, right?
Yeah.
You assume that you know the number of global models.
No, we start with a single global
you start
model,
with a single
which is an assumption that we do. We start with a single one. This is already in the middle of the federation. Okay, we already have 3 different models, but we assume all clients are in the same type of concept, which is an assumption of our approach.
Okay, and so it's okay if you. So in fact, your scenario is probably more of concept shift than concept drift, right?
Well, I don't.
In the way you generated it's a shift, not a drift, because you're not slowly drifting away from.
Oh, okay. Yeah.
Changing to another.
For me, those 2 terms were interchangeable.
Oh,
but maybe I'm not as familiar as I should be with concept drift.
Yeah, because in real life, typically it's not an abrupt change.
It's not an abrupt change. Incremental, gradual. Yeah.
And then you need to somehow assume that it's no longer the previous one. It's something.
But since we are considering that each time step receives a certain amount of information, we hope that the certain amount of information is representable. That
that's not a big deal.
Yeah.
And the other question I had, so it's okay. You can go back to the previous concept. That's okay. Right?
Yes, because you only need to identify with another model at another time step that is already in the set of global models. So we never eliminate a model unless it has been merged. When we merge these 2 models, and the identities of the models are updated according to that.
Okay, thank you.
Thank you.
Any other questions? Yes.
Thanks. How do you define unprivileged in the context of research?
So the unprivileged group is always context dependent and data set dependent. In the context of our work, we experiment with different data sets. Let me go back to the slide. We consider NIST, feminist, CIFAR 10, and adult. NIST, feminist, and CIFAR 10 are not even fairness-related data sets. So we need to simulate 2 different groups. And what we do is that NIST and feminist and CIFAR 10 are image data sets, but they don't have the sensitive human groups. So what we do is to create 2 different groups, we invert the background of some images. So for example, in NIST, we have a white background and the number in black, and we create another group with a black background and a white number. So that's how we simulate 2 groups. In the case of adult is already a fairness-related data set using the fairness literature. And basically what it is a data set where an algorithm predicts if a person receives more than, I think it's 50K per year or not. And what people have found was that this data set was biased towards some sensitive groups, particularly the age, and I think it was the race as well. So in this case, we experiment, I believe it's with the race, but I'm not sure. But you can use multiple types of sensitive attributes. But what we find is that the proportionate of positive instances is smaller for some groups than for others, and that's what we know that a specific group is unprivileged in that scenario, because received favorable outcomes by the original Y in the dataset.
Right. So the privileged just means that the algorithm treats those people better, right?
Yes.
Okay. So it's not
Because
that you always assume that women are unprivileged.
No,
Okay.
it depends always on the context.
Right. And do you study cases when the unprivileged group is a majority?
In this case, no, because our algorithm works better than other baselines because looks at group specific losses. So if the unprivileged group is represented enough, those overall loss metrics will be identifying those concept drift. In this case, we work in scenarios where the unprivileged group is a minority.
Okay, thanks.
Because otherwise, other algorithms would work quite well. But there are multiple things that we can explore here that we haven't explored that take into account what you just said. So thank you for the question.
All right. Any other questions? Okay, let's give another round of applause to Teresa.
Thank you.
See you in 2 weeks.